Our next speaker is Professor Tal Raviv. He is an associate professor of industrial engineering at the Ibi and Aladar Fleischman Faculty of Engineering at Tel Aviv University, Israel. So he has a BA in economics from Eitan Berkler School of Economics, Tel Aviv University, followed by MBA and a PhD in OR, Operations Research, from Technion. He has also been a postdoctoral fellow at UBC. He served as an advisor for startup companies. He's also editorial board member in Transportation Research Part B. And his primary research interests are in transportation and logistics with a focus on smart and sustainable transportation. So today he'll be talking about shared mobility systems. Tal, you can take over.
So thanks for the introduction and thank you for inviting me to this very interesting and diverse workshop. So hello everyone and good afternoon. The last few months have changed the view of many regarding the need for passenger transportation services. This event is just a demonstration of how the fact that we should rethink transportation services. Indeed, we all attend this meeting from various places around the globe, and none of us has to travel a single mile for this end. Yet, when the world returns to its new normal, I believe and hope that we will continue to travel because mobility is a fundamental social and psychological need of humankind. I can tell you that here, from where I'm speaking in Tel Aviv, the lockdown was partially removed only 3 weeks ago, and we already witnessed volume of traffic and congestion that is almost as severe as the situation before the pandemic. I chose a very general title for this talk, so let me first refine it. I'm going to talk here about one-way car sharing systems. So these services allow subscribed users to rent a car at any location within a city, use it for a single trip, and return it near the destination within the predefined service area. The check-in and check-out process are automatic and typically performed with the aid of a mobile app. The app also helps the user to locate the car for billing, etc. But before looking at shared cars, let us first take a look on the privately owned cars. And the first observation I want to make about privately owned cars is that they are very expensive. A person with an average salary in the US spends about 20% of its earning on using a car. And this ratio is even larger in less affluent countries. Most of the car ownership cost is fixed, cost that you pay regardless of your level of usage. The variable costs, on the other end, are relatively low, meaning that if you already own a car, any additional trip is relatively cheap. The traditional and most popular alternative to car journeys is using public transit. However, public transit systems typically cannot meet 100% of the transportation need of most people. Unlike private cars, they are limited in their geographical and temporal coverage. They are not suitable for traveling with a lot of equipment or staff and may not be useful in various situations. Therefore, almost anyone who can afford to buy cars, buy it. But here comes the paradox. Once they own car, they are likely to abandon public transit altogether because the marginal cost of using the car is competitive with the price of the public transit. And this is a vicious cycle. Higher tendency to own cars drastically reduce the demand for public transit. However, since there are clear economies of scale in public transit operation, the reduced demand for it leads to poorer service, which only increase the tendency to own cars, and this cycle repeats. So what's so bad about many people owning private cars The problem is that there are inherent inefficiency with private cars, and these inefficiencies are not mitigated by the market mechanism. If you own a car and you decide to use it for a particular trip, you have to bear some costs. You pay for the fuel and the wear and tear of the car. You pay for the time you waste on the road, especially if it is congested. These are your internal costs. But when you're using your car, you create more congestion on the road, which slightly increases the travel time of many other users on the road. Your contribution to the congestion is an actual cost incurred by other users. These costs are called external costs or negative externalities. Of course, there are other externalities that are associated with car usage, including greenhouse gas emission, local and air and noise pollution, and more. So when you and everyone else decide to use their cars, they consider only a fraction of the cost incurred by their decision. Therefore, the demand for car journeys is much higher than the efficient level that would be allocated in a perfect market where everybody consider the trade-off between the cost and the utility. The result is even more congestion, which everyone is worse off. Any economist since Adam Smith will tell you that in the presence of negative externalities, the government should intervene. This is well recognized by economists, and regardless of their ideological alignment. Governments do intervene in the transportation market, but it's often the case with governments, not always very effectively. So government may affect the transportation market either by trying to control the supply, to control the demand, or by increasing the supply. For example, the government can create alternative for private car users by subsidizing public transit, pave comfortable sidewalks and bike lanes, and recently also by supporting shared mobility programs. Shared mobility refers to various technologies that became popular in the last decade, but also have roots in other times. And in this talk, I'm presenting some finding and observation regarding one particular case of shared mobility, which is car sharing. And I will talk also on the currently prevailing car sharing systems, which are based on human-driven cars, and also about the futuristic version of car sharing, which will be based on autonomous vehicles, or automated vehicles, actually, I should say. So my first research question is, can shared car reduce congestion? And this question is trickier than it sounds. The main hope of the proponent of car sharing systems is that it is going to relieve congestion and other negative externalities by the following mechanism. The opportunity to use shared cars will cause many people not to own private cars. With shared car, the user pay the full price, variable and fixed for each trip, and thus they are incentivized to replace many of their car trips by one of these better and greener alternatives. Because the payment for the shared car is per use, the car ownership paradox I presented before is resolved. The shared cars will be used only for trips that cannot be served by other modes, but most of the time people will prefer a much cheaper alternative. However, in reality, if you ask users of car sharing and ride-sharing systems how they made their journeys before the system were available, most of them will answer that they use traditional public transit. Similarly, users of bike and scooter sharing systems switch primarily from walking. Indeed, the reality of shared mobility may not be so utopic as we would like to be. So again, can car sharing systems reduce congestion? So it is well documented that most of the early adopters of car sharing programs, as well as other shared mobility systems, did not have car before these systems were launched in their city. Therefore, the introduction of car sharing systems has no short-term potential to reduce congestion. To put it boldly, you cannot teach an old dog's new tricks. Bright side, however, is that it is also known that subscriber of car sharing systems has much lower tendency to purchase their first cars. That is, we cannot hope for many old car owners to switch to shared car, but the availability of a good shared mobility ecosystem surely deter many new drivers from entering the car market. And this observation goes in line with the fact that the tendency of young adults to own cars decreased over the last few decades. And a good shared mobility system can surely support this process. So car sharing systems come in two flavors, round trip system and one way. In a round trip system, each vehicle has dedicated parking spot. The user typically places an order in advance to rent a car. The cars are typically rented for several hours or even sometimes for several days and returned to the same spot after being used. Such system typically includes multiple types of cars to suit different users and different life situations. The service area of the system is large, and as long as the user returns the car to its place after using it, he can use it to drive everywhere he wishes to. The users are typically charged based on the length of the renting period and the total distance traveled. In one-way car system, on the other way, the vehicles are spread along all over the service area, which is typically limited to a city or metropolitan area. Users can rent car in one location and return it anywhere in the service area. Typical renting session consists of a single trip, and its duration is few minutes to few tens of minutes. The system offers one type of car, typically an economic compact car, and in many cases, an electric car. The users are charged by the minutes. And there are two types of one-way car sharing systems: station-based system, also known as A to B, where cars must be returned to one of the designated parking spots that are reserved for the system, and free float, also known as A to Z, where the cars can be dropped at any valid parking spot in the city. In the case of a free float system, parking spots that are reserved for the shared car may or may not be available. Is there any right topology for a car sharing system? I believe that each one has its own merits, and in particular, round trip and one-way systems can coexist in the same service area because they are serving different types of trips and needs. Station-based system may be a good solution for one-way system that based on electric cars in cities where the charging infrastructure is not developed yet, because they can be used, the designated parking spot can also be used for a charging facility. Station-based are also easier for the operator to maintain and rebalance, but they require allocation and reservation of many parking spots in the city, which is not always an option. As of today, most of the prevailing car sharing systems are A to Z, and I will focus them in this talk. So, to understand whether car sharing systems are a viable alternative for car ownership, we first need to understand the main challenges in operating them. So, operational problem number one is the inherent tendency of this system to go out of balance. The demand pattern is not symmetric in the short term, which is clear. For example, during the morning rush hour, many commuters travel from the suburbs into the central business district, while in the afternoon, most of the demand is in the opposite direction. Less intuitive is the fact that the demand is not balanced even in the long run. For example, it turns out that in many cities, the demand for trips from the center to the suburbs is higher than the demand for trips in the opposite direction. One of the explanations for this phenomenon is that the PM commuting trips tend to be more composite and harder to be replaced by public transit. For example, one may wish to stop at shopping center or a gym on the way back from work. As a result, we see accumulation of cars at the fringes of the service area and shortage of cars at the center. Therefore, the operator must take an action to rebalance the system. So one such action is to use dedicated team of workers that move cars from where they are accumulated to where they are in shortage. Such operation requires the workers to travel with an additional vehicle and driver between the locations of the cars. And this is a very costly and complex operation. At the end of the day, such a car repositioning operation typically enable one additional trip of one of the users, but require at least one additional car trip in the city and much labor. The economic and environmental sense of this mode of operation is questionable, and yet many car sharing operators do employ teams of workers that rebalance the system. Another possible way to rebalance the system is to use price incentives. Indeed, if the operator sets higher price for trips from areas in which the cars are in shortage, the imbalance can be eliminated. There are several interesting academic papers about this idea, but the method did not catch in practice. And it may be the case that the service provided by car sharing systems is perceived as an elementary public service, and the decision makers are reluctant to use price incentives that can be viewed as one that discriminate against the poor. But for free float system, the trouble do not end here. Even if the system is balanced, it is not clear that the distribution of the car within each zone of the city is such that users who need them can locate them and access them by a short walk. In fact, cars that are dropped by the last users in an inconvenient or inaccessible location are likely to stay there for a long period until someone bothers to pick them. Over time, large share of the fleet is likely to get stuck in such inaccessible spots. And this phenomena is well documented both by our simulation that I will present in a minute and by data that we collected from the operator. Of course, the second problem is also amended by the rebalancing measures I just discussed, but again, with their cavities. So a possible approach for understanding the dynamics and performance of car sharing system is to run simulation that is based on actual trips made by many passengers. Even ones made by other modes of transportation, such as taxi. In our experiment, we use a public data set with more than 1 million taxi trips in Manhattan, New York, collected over 6 months in 2016. One advantage of such analytic approach, other than merely looking at the transaction data of the system, is that we can follow not only the cars, but also the users before they located and check the cars. In the simulation model, we can also observe users that decided to abandon the system because they couldn't locate car at a reasonable walking distance from their origin. Note that the transaction logs of car sharing systems operator rarely contain information about the actual origin of the users, from where they walk, I mean. And they never contain complete information about the user who abandoned. In our simulation, a passenger uses the system if she can find a car at a reasonable walking distance from her origin and abandon it otherwise. If several cars are available, the passenger walks to the nearest one. When the passenger completes her trip, she leaves the car at her destination. The walking and driving time were collected from OpenStreetMap routing mechanism, and the travel times were adjusted to the traffic condition based on the information about the actual travel time of the taxi in our data set. By the way, I switched to the plural first person because this work is a joint work with a graduate student in Tel Aviv University, Miss Shir Tavor. The trips in our simulation were picked randomly from the data set based on the time of the day and the day of the week. Since car rebalancing is a problematic and limited practice, as I discussed, our first goal was to check whether it is possible to run car sharing system without it. To this end, the choice of Manhattan is very favorable setting, since this is a large CBD with no suburbs and a relatively symmetric demand for trips, which spread nicely over the day. So the condition of our experiment were as follows. We checked 3 demand levels with 5,000, 10,000, and 20,000 trips per day, which we sampled from the data set. We simulated several hundred of days for each of these conditions. Of course, we control for the warm up terms, but I wouldn't get into the details here. We checked 2 levels of fleet size. In one of them, we had 1 car for each 9 daily trips, and in one of them, we have 1 car for each 3 daily trips. So, for example, the 10K trips per day case, it was either 3,333 or 1,111. We assume that the user are ready to walk up to 5 minutes to reach a car, and the service area, as I said, was limited to Manhattan. Our results show that the idea of a car sharing system without rebalancing is nothing short of catastrophic. Even when the number of cars was third of the number of trips, only 87% of the passenger could find a car in the 5K trip per day scenarios. And although the situation gets a bit better when you scale up the system, even in the 20K trips per day scenarios, we also have we still have 8% of the passenger of the trips that could not be materialized. And the average number of trips per day made by each car was well below 3. And also the total walking time of each car was less, up to half an hour a day. Now, of course, we can improve the car utilization figures by reducing the size of the fleet. So, for example, for the 9 cars per trip, we see a much better utilization, but then the fill rate, the service level is ridiculous. We made some sensitivity analysis about our assumption regarding the willingness of the user to walk to other cars and other parameters here, but this did not fundamentally change the picture. The conclusion for now is that car sharing system cannot provide reasonable service without putting a lot of effort and resources in repositioning the car and without applying price incentives. The former solution is costly and the latter is unpopular with user and public decision makers. In light of these grim results, a natural question is why governments and cities and even private firms invest so much in deploying one-way car sharing systems. Our hunch is, at least when it comes to private company, is that they do so because they are expecting a new disruptive technology that will make their venture very profitable. And in the meantime, they want to create a user base that will use this future technology. This technology is driverless automated vehicle, or AVs for short. A car sharing system that is based on AV is actually more similar to ride-hailing service like Uber or Lyft. The user enters their desired trip in a mobile app, and the AV can show up to her location, pick her, and drop her at her destination. The main difference now is that the users do not need to walk to the car, and hence they can be served by cars that are not near them. So we ran similar experiment. But now we use a much smaller fleets. We began with a fleet of 9 cars per daily trip and increased this number up to 36 trips per car, and the rest of the conditions were left as before. And the results of the simulation with the AV is much more encouraging. Unsurprisingly, if we are ready to operate a car for every 9 daily trips, we can provide a perfect service, almost 100% of fill rate, and the average time for the car to arrive is short compared with equivalent taxi service. Each car is used 9 times a day, and is working about 3 hours. Note, however, that some of the working time of the cars is now not productive because they are deadheading empty to pick up passengers. And when we decrease the number of cars in the system, we sacrifice a bit in terms of the reliability and response time. However, the utilization of the fleet is fantastic, which means that the service can be provided at low cost. The implication of AV technology for car sharing and mobility in general is tremendous. Imagine reducing the number of cars in the city by a factor of 10 or 20, because each car serves 20 to 40 trips per day without decreasing the passenger traffic at all and without the inconvenience of public transit.
Well, if you can wrap up.
Okay. So I will just mention that the next step for us is to try to even rebalance the system even better by predictive repositioning, and we are working on such forecast and rebalancing optimization problem. The idea is that with AV, the rebalancing operation is very cheap. It just let each car, whenever it gets available, to predict the next location where it is going to be required and relocate to this location. So this is our mathematical model that solve, after having the predicted data, solve the online repositioning problem of the system, and I will be happy to discuss it on another talk. So to conclude, we showed that one-way car sharing systems are not likely to be economically and environmentally viable substitute for massive share of the trips as long as the driverless AV technology is not ready for the market. We see that many city do invest in one-way car sharing system, possibly because they are trying to create an holistic ecosystem where public transit is an attractive option for many other, for most of the at least new drivers. And having said that, I still believe that at this stage, cities should focus on round-trip car sharing systems that are much cheaper and simpler to operate. And there are many, so heavy car sharing are still futuristic, but it is not too early to start investigating the optimal operation and potential benefit. And I listed here some hot topics, but since I'm running out of time, I will be happy to discuss them offline with anyone who is interested. Thank you, and sorry for the delay.
Thanks, Tal. I think that was fantastic, very interesting presentation. So maybe I'll just post one question a couple of people have asked is regarding, if you have these car sharing systems, right, the private car buying will reduce, right? And what is the incentive for car manufacturers to push towards these kind of systems? Will it even see the light of day?
So indeed, this is an interesting problem. Car manufacturers, especially in Europe, already facing a decrease in their demand. They know that younger people tend to buy less car. By the way, tend to not to even get a driving license at a young age. And when they buy car, they typically buy cheaper cars. But they know that the market is going to change, and at the same time, there are a lot of new players that are not traditional car manufacturers. Google, for example, is in this market. So the incentive of the car manufacturer is try to secure some of the market and change from producing a product to providing a service. So this is the same servicization process that was mentioned also in the previous presentations.
Great, thanks. Yeah. So there are a few other questions. Maybe you can look at the Q&A, and if you want to type your responses, you are welcome to do that. So I think we'll move on to the next speaker. Thanks, Tal.
Thank you.